name is Fahrig, and I was the lead for Group 2 for Experiment 6, the commercial air conditioning experiment. So a little intro. In this experiment, we're going to be exposed to the equipment, controls, and programming found in commercial air conditioning. And then the experiment is going to focus on the theory and application of the variable air volume air conditioning boxes. So our objectives is for our students to understand the efficiency of an air handling unit, or AHU, the physical components of the air handling unit, and the variables in air conditioning equations. So for the theory of an air handling unit, the warm air enters the AHU and then passes over the cooling coil. The fluid then passes through the coil. It could either be water or refrigerant. That absorbs the heat from the air. The dry bulb temperature entering the unit, or ENT, is going to be higher than the air leaving the coil, the LVG. And typically the air being supplied to the room, or the SA, the supplied air, will be higher than the LVG due to the heat from the fans and motor. So more theory. The air handling unit is basically just a big heat exchanger. Some important variables we're going to need to know are the apparatus dew point, or the temperature of the cooling coil. Then we're going to need to know the coil bypass factor, or the CBF, which is the percentage of the air that doesn't get conditioned over the cooling coil. You can see right here, here's the equation. You're going to use the temperature leaving the AHU minus the apparatus dew point over the temperature entering the AHU minus the apparatus dew point, and the lower the CBF, that's going to indicate a higher unit efficiency. The AC unit size rating is the maximum amount of heat that can be absorbed by the AC unit. In this experiment, it's going to be 5,000 BTUs per hour. Then the electrical input to the AC unit is the amount of power that's being used by the AC unit. That's going to be 580 watts for this experiment. Other indicators of efficiency are going to be the energy efficiency rating, which is the AC unit size rating over electrical input to the AC unit, and the coefficient of performance, which is just the energy efficiency rating over 3.412. So the real world application of this variable air volume box is just a simple mechanical device. It's consisting of a damper and an actuator. The damper is going to be able to be opened or closed to satisfy the space conditions. And then we can change the amount of heat removed from space by changing either the airflow to the space or the temperature difference between the room air and its supply air. So some important equations we're going to need to know to calculate our results. We have the rate of heat removed from a space, which is Q dot equals to mCp, or mass flow rate, times specific heat capacity times the change in temperature. Or substituting in, we can find that for this experiment, we use air, and we're going to have that equal to 1.08 times the volumetric flow rate times the temperature, the change in temperature. And then the rate of heat gained or lost in a space is going to be the change in temperature times the area of the space over the thermal resistance. So the scope of the experiment, we're going to focus on thermal resistance of four things. We're going to focus on the outside surface temperature, which is the convection thermal resistance between the outside air and the building surface, the air gap resistance, which is the resistance found in the air gap between two or more surfaces. The air gap acts as an insulator. Then we're going to need to know the internal surface resistance, which is the convective thermal resistance value between supply and room air. And then sheet metal, it's basically just the conductive thermal resistance between the two sides of the piece of sheet metal. So for our apparatus, we're going to have the cooling loop apparatus to start off with. The air enters the AC unit and it ends at the diffusers down here downstream from the VAV boxes. It draws in the lab air and then passes over the cooling coil, which is inside the AC unit. It's then drawn to the supply air fan and then sent to the supply heater, and then it just goes to the ductwork between chamber A and B. So the heating loop apparatus, the warm air enters the heat loop fan. The heating loop apparatus is also a closed loop. The air is then sent downstream to the heat loop heater, and then it's sent to the hot plumb between chamber A and B. The chamber A and B apparatus, the chamber A plenum and the hot plenum are the same. Between the hot plumb and chamber A, we're going to have three types of resistances. And between the chamber B and hot plenum, separated by a 1-inch air gap, and there's going to be 5 types of resistances. Some safety guidelines for the experiment: don't touch the ductwork because they're going to be hot. Don't touch the insulation. Never turn on either of the heaters without the appropriate fans operating, because that's going to cause the heater to burn up. And then be aware of the nearest fire extinguisher in case a fire were to happen, and just remain clear of all the electrical components. So for our procedure, we're going to just rely on the backtalk program. The recorder is going to have specific results and values it's going to need to tabulate in Table 2 and Table 3. And after everything's done, after we conducted the experiment for 30 minutes, we're going to have to turn off the cooling loop fan and the heating loop fan and turn off the AC unit. And for our expected results, since we have only 3 resistances for the chamber A, between chamber A and the hot plenum, that's going to end up being the total thermal resistance of 0.93. And then as an example, I used the change in temperature as 30 degrees Fahrenheit, and then the area of the room as 20 feet squared. And that'll give you around 645 BTU per hour for the heat removed from the space. And then manipulating the equation, we're going to get a volumetric flow rate of about 0.33 cubic feet per minute. And as you can see, there's 5 resistances for chamber B, and this ends up giving us about half the values that we got for chamber A. So that should be pretty intuitive. And